invite me here. It's a great place to be. The talks are all very interesting, and mine is only, you see, tangentially related to machine learning. I will make some comments. I want to first of all put down the bibliography. So this is a joint work with Carmeli from Genova and Varadarajan. So this talk is based on two works appeared, one in transformation groups this year, and the other one appeared in Universe last year. And in the organization of the talk, I will start first with the superbundles and then move, if time allows, to the Harish Chandra supermodules, which are far more technical. So I want to spend a few moments really very fast to talk about supergeometry. And of course, I mean, if you're not familiar with it, don't worry. I mean, it's not, the talk is about supergeometry, but I will try to convey ideas through examples. So what is a super vector space? A super vector space is Z2 graded, so it consists of an even, what's called an even space, V0, direct sum with V1. And the main example, and one can really limit to this, is Km plus Kn. And we say it has dimension m/n, but truly it has dimension m plus n, of course, as a vector space. But as a super vector space, we look at the dimension as a pair. And the field K, it is either R or C. Of course, it's possible to generalize, but we don't need to be more general at this stage. This definition is motivated from physics, where the fermions are particles that behave according to the Fermi statistics, while the bosons according to the Bose-Einstein statistics. And in this case, we call them odd and even. And so they belong to V1 or V0. And the key point I wanted to make by giving you a little physical motivation is to say that supergeometry is born by the desire of looking for new symmetries. And it seems that in this conference, symmetry is a central point, and you want to understand what really symmetry means. So superalgebra is just a super vector space with a product that respects the parity, and we say this commutative, and this definition categorical is due to the line, is happening when AB is equal to -1 parity of A, parity of B, of BA. So just to give an example, if you take x1 and xm, and I write the Latin letter to mean that these coordinates are even, so they behave like a usual coordinates. So see, in this case, x1, x2 is equal to x2, x1. So they form a symmetric algebra, while the xi1, xi2, and so on, they are written with Greek letters and are odd. So when you do xi1, xi2, you get equal to minus xi2, xi1. So in particular, xi I squared is 0. So these are belonging to an exterior algebra. So a commutative superalgebra is not really commutative. It is something weird that has a commutative part and an anti-commutative part, again, behaving exactly as the wave function for a particle. Supermodules are modules over commutative superalgebras. And I just wanted to, so a free supermodule is written as AMN, it's just a superalgebra, and all the algebras we're looking at will be supercommutative. So it is a tensor product, and it will split in two parts, A0, which is the zero part of the algebra A and the zero part of the vector space, plus the one part. So it is really behaving nicely, because 1 plus 1 is equal to 0 in Z2 gradation, and the one part is this. So now there is some categorical interpretation, which I really try to keep at a very minimum, but in order to enlighten the Kotzul key contribution to this field, I really need to show you how ugly this was before Kotzul put some order into this. So this is, well, ugly or beautiful, it depends on the beholder eye, but let's say that if you're looking at a functor of points, the truth is that you need a machinery coming through categories. So you interpret a supergroup, the super general linear group, as a set of matrices which have values not in the field that we are considering, but in some superalgebra. Which superalgebra? Just pick any. So you get a collection of groups. So you have GLMN for A, and A is any superalgebra. So you're really a collection of all these objects, and the collection of all these objects will define what is the general linear supergroup. And if you're like me, you find this a bit disconcerting. And so there are examples. Physicists, however, found this way in this, I think it was around the 70s, 80s maybe. They were writing these objects where they would take as their A exactly that algebra that I was writing to you in the previous slide. Without realizing they were doing the functor of points, they would do this, so they would not be so worried. And now comes I write it as the last line, but by no means is last. You can interpret the supergroup G as what is called the super Harish Chandra pair. So this very cumbersome object that is appearing with this a collection of infinitely many groups, here you can understand it simply as a pair consisting of G tilde, which is just a Lie group, an honest Lie group, and G is a Lie superalgebra. Lie superalgebra are Z2 graded algebras that have been studied and classified in some mild condition by Katz, that was in the 70s, and they were well understood. So Kotzul's key idea is exactly this. I replace a very complicated object, this functor of points, which you don't really know what that is a set of morphism in the category of superalgebras, something very ugly, with just a pair of objects that I know very well. So a Lie group and a Lie algebra, provided some conditions are verified. So just not any pair, of course. For example, you want the Lie superalgebra, its even part must be the algebra of G tilde. And then you can look at representation. So this, by the way, it is strange enough, was communicated by Kotzul when he came to visit Bologna, my university, in 1982. But I was too little, so at that time I was in high school, so I could not meet with him and did not realize, I mean, at that time, of course not, but only much later I realized that this interesting conference happened in 1982 at my university, was holding the key to understand all these very interesting problems. But this paper of Kotzul, I really urge you to see. In 1982 is basically you cannot find in any, so ask me to get it because it's hidden in some obscure proceedings of Bologna, blah, blah, blah. So it is contained also a very interesting treatment of the exponential map for a supergroup. To my knowledge, even nowadays, after this treatment of Kotzul was given, there is not a better treatment. So he really was much ahead, 1982, and now we are not, we're still exploiting all of these ideas in these few pages that he gave. So let's see what is a representation. So again, I will show you how the idea of Kotzul becomes really important when you want to do something with supergroups. So if you want to see the action of functor of points, that's really beautiful because it's very simple. It's simply, I mean, beautiful in the sense that it's very natural. It's just action, but you have to consider it's infinitely many algebras, and that becomes complicated. Or you can look at the natural transformation. Very elegant. The linear does it, but you can't do anything with it. Or you can do what Kotzul does and understand a representation of what is called a super Harish Chandra pair representation, which looks at the beginning a little ugly, but let's look at it together and convince ourselves that it's not ugly at all. Because if you look at representation of a supergroup as a pair, see, you have a representation of G tilde, but that's a Lie group. So representation of a Lie group, we know what that is. It's very simple. I mean, it's been known for over a century now, I think. And you also have a representation of a Lie algebra. Great, we also know what that is. And then you have a compatibility condition. So you see that this third bullet is putting into apparently more complicated equations, but in truth is putting something very strange that we don't know what that is into something we can compute. And if you look at papers in supergeometry, sooner or later, at some point, when they look at the symmetries, they will go to this Harish Chandra pair approach, because that's really what you should do. So now we come to the work that I did together with Carmeli and Varadarajan. It is only natural to try to see what is a supervector bundle is. Okay, so supervector bundle, it is no effort. You define it as a locally free sheaf. I mean, it's something you attach, so you have a supermanifold. I don't want to say what that is. Think about a manifold is the same, and then at each point you attach a supervector space. That's really what it is. However, we want to push it a little further and construct what is called the associated bundle. So if you give me a representation of a closed subgroup of a Lie group, you can give me the associated bundle, right? Which is the H-invariant sections. Now, if you give me the function of points language, you can do it. See, it's ugly. I don't want to go into this technicality, but you have to do it for all these strange algebras. Supergroup language, you can do it also directly looking at the dual maps. The super Harish Chandra pairs, it's even uglier. I don't want to give meaning about this because it will take too much. But what I'm trying to say is that in my very short introduction to supergeometry, what we have been doing with Varadarajan and Carmeli, showing that this strange functorial language is actually equivalent to the super Harish Chandra pair language when it's coming to associated bundles. Associated bundles are fundamental if you want to study representations, because both finite dimensional representation, but especially infinite dimensional ones, I realized in the vector space of sections of the bundles associated according to some character. So this equivalence, I did not want to spell it because I didn't think it was fair, since I was not explaining all of the symbols, but this is the super bundle paper. Now I'm setting the problem, discussing more what I've been doing in the transformation group paper, which is the one that I summarized into into the proceedings. So you take a simply connected Lie supergroup, and then you take a basic complex Lie superalgebra. So think about, for example, a subgroup of GL and the corresponding superalgebra. And then you take a real form of the group. Believe me, as you can look at the real forms of Lie groups, you can look at real forms of supergroups. And a real form of the Lie algebra will be the Lie algebra of the real form of the group. And then you take a maximal torus, and then there is the corresponding Cartan subalgebra. In the generality, this can be also super, but in our problem we consider it to have just the even part. And then there is the KR. So this is the maximal comp that Professor Barbaresco was talking about. You know, you can form the quotient GR mod KR. So SU11 mod the torus. That is what we've been doing. And so this is part of the theory. And what you can do, if you pick a character, there is one last assumption which looks innocent, but without this we cannot make it work. So you have to take the Cartan subalgebra to be such that is both the Cartan of the compact K and the Lie algebra. for the case that we saw in the example of SU11 mod the maximal compact, this is the case in that example. In general, it may not be, so there may be situations where this is not true. And then we pick an integral weight. So we pick an element of H star which is integral. I don't have the time to explain what that means. It's, it's like a standard condition. And then we form the character chi of the torus, which is, defined in that way. And then we form the associated bundle. And we look at the sections, okay? So that is the key. So we take G, we take the root space decomposition, we define the Borel subalgebras and the nilpotent really in the way that everyone expects. I even put a small example to show. So I look at the case of SL11. So that is the complex case with this B plus and N plus. When you're looking at root space decomposition, you need to go to the complex word, otherwise you will not see the roots. At least you don't see them in a nice way as otherwise. And then what we've been trying to do is to construct exponential diffeomorphism. And again, this Kotzul comes and helps us because, as I said, the exponential for super word is not the exponential. So, exponential is never simple, but for supergroups it's very complicated. And we want to obtain global coordinates. These global coordinates, both in the super and non-super world, are key to construct the representations. And I know many of you are not interested in supergeometry, but believe me, even in your world, if you look at these global coordinates, I'm sure I'm telling you stuff that you know very well. The nilpotent N plus and N minus, this polynomial algebra will be a representation of the Lie algebra of your group. And this representation is Fréchet dense. So it will tell you a lot about the representation of the group when the group is infinite dimension. So I have to quote a result which is very technical. So if I look at a certain functor gives me a full and faithful embedding. I have to say this because otherwise what I'm saying next is not correct. So if I take a complex matrix supergroup as above, because we take our group to be a subgroup of GLMN, then the GK0N, so K0N is a special superalgebra, commuted superalgebra, corresponding to an exterior. That's a notation for the exterior algebra. I should not have written a different notation. This G is an analytic Lie group, and the corresponding Lie algebra is an ordinary Lie algebra. So we extract from our supergroup a true Lie group, and the exponential is really a morphism of lambda 0 manifolds. So this is our first result. Now, the second proposition is that the exponential morphism, now here, notice that we're not putting GK0N, but if we take the nilpotent supergroup as above, so it is a subgroup of our G, then the exponential morphism is a global super diffeomorphism. So this generalizes what is well known in the Lie group setting, and this will give us the coordinates that we need in order to construct the representations. So the next step we're taking after proving this result, which I put in detail in the proceedings, is to discuss after this is known, so after you get these global coordinates, how to construct how much time do I have for the representations? Very little, right? Three minutes. So I'll be really fast. I will skip many, many facts that you can find in the proceedings. I want to go straight to the main theorems. I'm sorry, I'm going very fast. There is a Fréchet structure. This Fréchet structure behaves extremely nicely, as I said, the polynomials are dense in the L chi are the global section of the associated bundle. I define what Harish Chandra module is, but I will not go into this. So let me go very fast. So the theorem that we prove first is that there is a non-singular UG pairing between the polynomials in the global exponential nilpotent coordinates and the Verma module, V lambda. So you have sections of a line bundle given by a character, which is the exponential of lambda. And then you establish, thanks to these nilpotent coordinates, a perfect pairing between this polynomial and the Verma module. As any Verma module, it has an irreducible quotient. Since this is a pairing P, which is a polynomial algebra in the nilpotent coordinates, will have an irreducible submodule, right? So a submodule corresponds to a quotient. So the submodule generated by the polynomial 1, I mean, of course, this algebra of polynomial, there will be the polynomial 1, is irreducible, and it generates the irreducible submodule P. So this one is the dual to the highest weight of the Verma module. So this is action of UG. So let me just quickly conclude. So this is action of the infinitesimal part, but this is unique, of course, because Verma is, we have also a global result. So this is also the theorem before was Carmeli and Varadarajan. I don't want you to think it was just mine. It's same, should say also there. So this theorem essentially said, hey, what we did in the previous theorem for the G Lie algebra, we are able to do not just for the Lie group, but for its real. So we are able to construct inside these sections of the line bundle an infinite dimensional representation of GR, and in this representation the compact acts finitely. So of course, being compact, it will split in infinite representation, but the sum of those that have same isotypic component, it will be finite dimensional. This is what is Harish Chandra. Okay, I think I will stop here. There were an example, yeah. I just put here, I did an example of the Siegel superspace, but I don't have the time. Thank you very much.